extreme values. So in sports, you have extreme sports. In mathematics, we have extreme values. Now, there's two parts to this section. The first part is extreme values, and the second part is Lagrange multipliers. Now, again, they're extensions of what you know for functions of one variable, but you need to be careful. It gets a little bit more subtle and a little bit deeper. So don't assume that if you have a good knowledge of maxima and minima for functions of one variable, that you'll just be able to understand this straight away. It's not quite like that. So what we're going to talk about today, we're going to motivate the subject. We're going to define what we mean by maxima und minima. And we're going to talk about critical points. Okay. And again, this is all for functions of two variables. All right, so let's motivate the topic. As I'm sure you know, many problems in not just applied mathematics, but applied sciences, engineering, and so on. These kind of problems can be mathematicized in the context of determining maximum or minimum values of a functions. And we're going to look at the several variable case. So what's a simple example? Well, think of designing a cylindrical silo to maximize its volume, but I guess the constraint is you're working with a fixed amount of building material. Now, this is a pretty simple problem that you may have come across in other contexts. So let me just sort of, you've got it. You can draw a badly drawn silo, and you know that the volume is given by pi r squared h. You want to maximize V subject to the amount of building material used. So suppose it's got a top and a bottom. You could so this length here is going to so for that problem, what you would want to do is maximize V subject to the constraint A, where A is some number. So you might have 10 square meters or 100 square meters if you build 1,000 square meters if you're building a big silo. Okay. Who's seen some sort of problem like that before, maybe at school? Or yeah, okay, some people have. So we're going to look at that in more depth. Okay, we're not just going to solve a reasonably simple problem like that. We're going to solve some hard problems. Now, at school, you studied how to find extreme values. What I mean is max and min values of functions of one variable. And it came down to, anyone remember? You looked at you take the derivative and set it equal to 0 and you solve, and then you can use a second derivative test, right? Well, it's similar in the case of functions of two variables, but there's a few twists and turns. It's actually more complicated, okay? In particular, we're going to use partial derivatives to help us out, both first and second order. Okay, so the big question. What are local maxima and local minima? Now, people, in my opinion, students think they understand what these things are, but they don't really. Okay? This is like a definition. Doesn't involve any calculus. Okay? It doesn't involve any calculus, these definitions. Okay, so let F be defined in some region R containing our point of interest. when we say f at our point of interest, f at a comma b, is a local max value of f, we mean that this value is greater than or equal to all other values for some open disk centered at our point of interest. Okay, so what this means is we can when we say f has a maximum at a point a comma b, our point of interest, we mean we can draw a little disk around the point of interest, and within that disk, this value is greater than all other values. Okay? When you say f has a local minimum at the point a comma b, it's basically the same, but you just reverse the inequality sign. Okay, so let me give you an example. Oh, by the way, when we don't like to use local maxima and local. We don't like saying local maxima and local minima all the time. To sort of compact things, we use the term local extrema. Now, let me give you an example. Suppose this is our function. Now, I'm going to claim. Well, let's. Yeah, no. I'm going to claim that f of 0, 0 is a local min. Well, let's try to put that into context. What kind of graph is associated? What kind of surface is associated with this function? What is it? Paraboloid, right? Now, at our point of interest, I can draw any little disk around the origin, right, in the xy plane. So I can draw some disk. So let's say it's 1, 1. Now, for all points within this disk, so think of it sort of as lying down here in the xy plane. For all points in that disk, f is always greater than or equal to 0. That means that this is satisfied. Okay? So let's call this D or something for disk. Okay, now you may look at that and go, well, duh, I knew that. That's fine. Yeah, it doesn't hurt to verify that the definition actually holds, okay? Because there'll be some cases where you'll be looking for max and min, and maybe the partial derivatives don't exist. You're going to have to use other methods. Okay, so that's a basic example of what we mean by a local min. Now, this is also, I guess technically speaking, it's not only a local minimum at 0, 0, it's also what we call a global minimum, because for all x and y, not just in this disk, but everywhere, the function is always greater than or equal to 0. So this is also what we call a global minimum. Okay, so here's another one that I prepared earlier. Here's a exotic function here. It's been plotted using Maple. And if we restrict the domain, in this case to a rectangle, I mean, I know the previous definition had a disk, but this is just a rectangle. You can show that it has a maximum value of 1 here and a minimum value of about negative 0.067 for all points in that rectangle. Okay, so let's sort of build on our intuition. There's a really, I guess the last couple of graphs hopefully have sort of given you a taste of what we mean geometrically when we say a local max or a local min. Well, have a look at the following surface, just a general surface, right? When we talk about a local max, it corresponds to one of these mountain peaks. When we talk about a local min, we're talking about a valley bottom or a valley low down here. And you can see, again, it comes back to drawing these little discs. Imagine though, these are drawn in the XY plane, technically. Okay? So when we're working within this disc, this is the actual sort of highest point within this disc. And then if I draw another disc around here, then that red dot is the highest point in that disc. Okay. Now this is important. Just like we can with regular calculus of functions of one variable, you can use partial derivative, or you can use derivatives, first derivatives, to determine these local extreme values. So here it is. What you would expect. Suppose that we know f has a local max or minimum value at some point, a comma b, in the interior of its domain. In addition, let's assume that the first partial derivatives of f exist at that point. Under those conditions, the derivative and this derivative at the point must be 0. Now this is an important concept, but how can I put this? Let's look at it geometrically. Essentially what this says is that at local extremal points, the surface has a horizontal tangent plane, provided, of course, the tangent plane exists. So in the picture, you've got this sort of light browny surface, and there's our point of interest. And the blue curves are just the intersections with the vertical planes that run sort of parallel to the appropriate coordinate planes. So you can think of this curve here as being, say, g of x, this curve here as being, say, h of y. And then you can use what you know from school about functions of one variable to show that these derivatives are actually 0. Now, if you take those derivatives and try to form the equation of the tangent plane, you'll get the following. Z equals, well, the partials are all 0, so it'll just be this. It's just a constant. Okay, so let's move on to talking about critical points. Now, from a computational method point of view, this slide's very important. We define a critical point of f in the following way. The two first partials are 0, or the two partials don't exist under either of those assumptions. We call the interior point a critical point. Now, I've got to say, this is the important one for our study. Okay, that assumption or that situation is important for us. We're not really going to spend much time considering the case where the partials don't exist. Okay, so from a practical point of view, this is important. Now, if we combine the first derivative test with our new definition of a critical point, then we can conclude the following. The only points where f can assume its extreme values are at critical points or so-called boundary points. So by boundary points, I mean points on the sort of edge of its domain. We'll look at both of those cases. All right, determine the critical points of the following function. So this is a relatively easy example. So here the domain is just all the xy plane. Okay, so to solve this, to calculate the critical points, we just take the partials and set them equal to 0. So we're going to solve the following. So we're going to get two equations and two unknowns. Two equations, two unknowns. Yep. Okay. So let's calculate these partials, set them equal to 0. So we're going to get, what are we going to get? Y minus 2x minus 2 equals 0. And x minus 2, hang on, let me start. Minus 2y minus 2 equals 0. So we've got two equations and two unknowns. So now we want to solve for x and y. The x and y will give us our critical point or points. So let's sub one into the other. Okay, how have I done it? So I've made x a subject over here and then plugged that back into the first equation. So I've eliminated the x's. So if I make x a subject and just sub in there, I'll get something like this. How about, yeah, it should be a plus 2, right? So, plus 2, yes, thank you. Okay, so solving that, then I'll get some value for y. So I can back substitute that into one of those equations. And according to my calcs, I get minus 2. So our critical point occurs when x equals -2 and y equals -2. Now, can I get you to take your hood off? Is that okay? Any reason why you're wearing it? It's cold, really? Okay. Yeah, I know, but okay, I understand. That's good. That's a good response. Now, there's only one critical point for that problem, but you can get problems where there's more than one. Okay, let me just squeeze another example in there. Okay, so don't worry, this won't take up much room. Okay, now note we've got 3x cubed in this. To find the critical points, we just, again, differentiate, set the partials equal to 0. Okay, so we're going to get 9x squared minus 9, set it equal to 0. And sub y is going to be 2y, set that equal to 0. So for that one, obviously y is going to be 0, so there's only one y point. But if we solve the other equation, we're going to get two values for x. So we've got two critical points in this case. And of course, you can go and get more critical points, 3 critical points, 4, 5. Probably wouldn't ask you to calculate 5. Okay, that'd be a bit mean. Now, the method, as long as the partial derivatives exist, the method for these problems are always the same. Okay, calculate the first order partials, set them both equal to 0. You'll get 2 equations. Solve those. Okay, be careful when you solve them. The biggest mistake that students make is that they're not careful when they're solving the problems. You could see, I should have had a +2 instead of a -2. So it's easy to make a mistake. All right, let's look at another important case. Calculate the critical points of this function. Pretty easy to do. We've seen this function before. So we calculate our partials, set them equal to 0. So our critical point occurs at 0, 0. But look at the graph. Look at the surface. That's where our critical point occurs, and the value of f at that point is 0. So can someone tell me why isn't that a local max or a local min? If you look at that, we've got a critical point, but this sort of example is designed to show you that a critical point, it may lead to a maximum, may lead to a minimum, or in this case, neither. Why isn't the origin a max or a min? Anyone know? Ah, now you're talking. Okay. Well, if I draw any little disk in the xy plane, right, I've got points in that disk where the function's always positive and the function's always negative. If I approach, exactly as you said, if I'm on this sort of light blue sort of parabola, as long as I'm not at the origin, x is going to be 0. So I'm going to get, my parabola is going to be something like y squared. As long as y is not 0, it's got to be positive. Along this yellow parabola, y is equal to 0. So I'll get minus x squared. My parabola is going to be minus x squared. As long as x isn't 0, minus x squared is always negative. So we conclude that our critical point, it doesn't lead to a local max and it doesn't lead to a local min. It's something else called a saddle point. Now, a saddle point is like when you were back at school, you saw points of inflection for functions, right? They didn't go like this, they didn't go like that, they went, like that, or like that. It's like the 3D version of a point of inflection. Now, saddle points can look like all sorts of types of functions. They don't always look like this, okay? But this is just a nice sort of, you can see where the word saddle point comes from just from this graph because it looks a bit like a saddle. Okay, so how do we define a saddle point? And this is kind of what I was saying with the disk before in that previous example. So a differentiable function f has a saddle point at some critical point if in every open disk centered at the critical point there are points where the function's greater than the value of the function at the critical point and vice versa. So here's some more examples of saddle points that don't really look like saddles. But the best, the easiest way I can kind of explain it to you is think about saddle points as just generalizations of points of inflection. That's the best way to do it. Okay? All right, here's one I've created earlier. Finding local extreme values. Find the local extreme values for this function. We've already looked at this in a sense. So you calculate the partial derivatives. They exist everywhere. So the local extreme values occur where the partials are at those x and y points where the partials are equal to 0. Okay, so we solve those. We get the x equals 0, y equals 0, and you can see from the picture, or even just through algebra, that the f of 0, 0 equals 0. That's a local minimum. And like I said before, this is also a global minimum. So it's certainly a local minimum, but it's also what's known as a global minimum. Okay, so today we've learned how to calculate the critical points of a function. Once we know the critical points, we can then go on further and try to classify them. So does the critical point lead to a local max, a local min, or something in between, like a saddle point? For that, we're going to use the second derivative test. Now, this is a pretty comprehensive test. I'm not going to talk about that today. We'll talk about it on Mondays.